Right. So we are discussing chemical bonding, right? The most important thing in chemical bonding is your perception regarding the bond. As I was always telling, and I would like to remind you throughout this chapter, that bond is basically a force, right? A force that binds two ions or atoms in a molecule, right? And remember that when you term the bond to be a force, then the force cannot be a single type. It can be an electrostatic force, it can be a covalent force, it can be an induced force, or it can be a metallic force. Depending on that, you have several types of bonding. And we have gone through very detailedly, very detailedly regarding what? The ionic bond. And now we are discussing covalent bond. Now with the prima facie, I just wanted to compare the ionic bond versus the covalent bond. The best feature of the ionic bond is it is so convincing. Now when I say convincing, in what aspects? Remember that, you know, the strength of the bond, ionic bond, seem to be absolutely naturally derived. Because in ionic bond, the ionic substances are made up of ions. That means you have a positively charged ion and you have a negatively charged ion. Right? Between a positive and a negative, you always have electrostatic force of attraction that is giving the strength to the bond, and they are bound together. That's the point. You must understand. So the strength of the ionic bond is basically derived by the cation and an anion and their existing an electrostatic force of attraction. This is what is the convincing explanation if someone is asking you, where does the strength of the bond for the ionic bond come from? Right? So it is so convincing. It is like this. You have cation, you have an anion, and you have electrostatic force of attraction. This binds these two and an ionic bond is formed AB. It's so convincing. It is so convincing. That's not the case with covalent bonding. So I would like to remind you, you know, you have a perception towards covalent bonding. Two atomic systems combine to give you a molecule, and there exists a covalent bond. And how do you explain this? Is basically the atomic systems are not getting their octet. The atomic systems are not getting their octet. So what they do is, in order to get the octet, they try to share the electrons, right? And the shared pair is put at the center. And the shared pair is basically put at the center and they both share. So that is how the covalent bond is formed, that you give one electron, I give one electron, we both put it at the center and we both try to share. For example, you see here this is the fluorine which belongs to the 7th group. It has given one electron, it has given one electron, so this is 2, 3, 4, 5, 6, 7, 8. You can see the octet. 8 electrons for fluorine. Fluorine belongs towards 7th group. So total number of electrons in the outermost shell is only 7. So it is not getting octet. So it is asking the other fluorine to come down. You contribute one electron. I contribute one electron and we both get octet. Similarly, this is also getting what? Octet. So this is 6 and 2. So this is 8 electrons. This is called the shared pair. This is called the shared pair, and both are achieving octet, and this is how they live happily. This is the story. Right? Remember, all this is fine. All this is absolutely fine. But we wanted to know, where does the strength for the covalent bond come from? I wanted to ask this question. Where does the strength for the covalent bond come from? It's so easy for us, so convincing for us in case of ionic bond. You have oppositely charged ions and you have electrostatic force of attraction that is actually binding these two. And when it's binding to that is the strength of the bond come from the electrostatic force of attraction. But the same explanation you must be giving it to even covalent bond most convincingly, which is not the case when you say that, you know, in order to achieve octet, people are sharing the electrons and a bond is established. It's fine, a bond is established through sharing. But where does the strength come from must be answered, right? So for that, I think the concept of overlapping has been introduced to you, and it was introduced first why? So to understand why the concept of overlapping, why overlapping? So let me put it properly. Why overlapping? Why overlapping is to explain where does the strength for covalent bond come from? So why someone is introducing the concept of overlapping, you must be clear. So we must be in a position to explain where does the strength for the covalent bond is coming from. So for that, I introduced the concept of overlapping. Now, one prime thing one must understand is basically, you know, if fluorine is forming a bond like this is the single bond between fluorine and fluorine. And if the concept of overlapping was not there, so our perception would have been, it is absolutely like this, that the fluorine atom is coming from this side, the fluorine atom is coming from this side, and they both are overlapping with one another, and you know, that's how the bond is formed. It is not the atoms that are overlapping. The atoms don't overlap at all. The atoms don't overlap at all. The atoms don't overlap at all. Don't be in that misconception. So basically, these things which are addressed at the micro level are nothing but the valence bond theory or the concept of what? Overlapping. You must understand that, right? So why did we introduce the concept of overlapping? Why overlapping is being introduced? To explain where does the strength for the covalent bond come from. And how are we explaining this? Observe. Now, if you wanted to explain where does the strength come from, then understand what I'm referring to is basically this. Overlapping, he is speaking of SS overlapping. Let us quickly check it out because this was told in the last session, but I think let us have a brief about it. SS overlapping. In this, you have an s orbital, you have an electron here, right? This electron is dynamic and moving through always in this particular area, and it looks spherical. And remember, this is s orbital. It's basically an s orbital, right? So this electron which is present in the s orbital is localized to a particular area, right? It's roaming around in a particular area. Now what we are telling is, if you wanted to overlap with another s, which is actually moving like this, and this is s orbital, mind you, they both overlap, and finally you get this, and you have now larger area to roam. So these two are atomic systems. Those two are atomic systems where the electrons are localized, and when they overlap, you get a larger area for what? For what? You to roam around. So when people are roaming around on a larger area, you lose more energy. You lose more energy. When you lose more energy, you gain stability. That is where the strength of the bond is coming from. Understand that. So overlapping has been proposed to explain the strength of the covalent bond. The strength of the covalent bond, where is it getting from? So if you wanted to explain this, it is, first of all, understand that it is the orbitals, not atoms. It is not atoms. It is the orbitals in an atom. It is the orbitals in an atom that undergo what? Overlapping. That undergo overlapping, and in the process of overlapping, energy is lost, and thereby they gain stability, hence a bond is established, and the strength of the covalent bond has been derived. So two things keep out of your mind, that atoms are not overlapping. It is only the orbitals in the atoms that are actually overlapping, and in the process they get a much bigger orbital. That's nothing but a molecular orbital where they are more roaming around, and thereby they lose energy. When you lose energy, you're gaining what? Stability. You must understand that. Well, you are writing an aptitude test. You're writing an aptitude test. That's your JEE or NEET. All these are basically aptitude tests. So to write an aptitude test, the concept is very, very important. The concept is very, very important. So the way we actually pursue things and the perception what you have towards that science will actually result in the aptitude towards science, and finally you write your aptitude test. So the concept is extremely important. What I'm telling is, you know, it's not convincing as ionic bond where the strength has been derived. For covalent bond, you must be explaining where the strength is coming from, right? And the best way to explain the strength coming from is the concept of overlapping. And this concept of overlapping is not for atoms. It is rather the atomic orbitals which are present in the atoms, right? They are getting overlapped. and then the strength has been derived because the energy is lost. Energy is lost, you get more stability. So atomic systems are less stable compared to molecular systems, because in atomic systems the electrons are localized, whereas in the molecular systems they are delocalized. Any delocalized system, I think, results in loss of energy. When loss of energy, you're gaining what? More stability. So what we do is, we just go in and pick out two of the points which are proposed by the valence bond theory and apply it to the molecules, and so beautifully explained is the valence bond theory. Observe carefully, right? Observe. This is what I mean why overlapping has been introduced, is basically to know where does the strength for the covalent bond come from, right? And this is basically the valence bond theory. The valence bond theory. This is proposed by Mr. Linus Pauling. Linus Pauling. And what we do is, we will take example and thereby explain how the bonds are formed. So two important aspects of valence bond theory is, one, a covalent bond. I wanted to repeat the postulates and listen to me carefully, right? A covalent bond is formed by the overlapping of atomic orbitals. Why he says this? Why he says this? A covalent bond is formed by overlapping of atomic orbitals. He is insisting on that. It is the atomic orbitals which are involved in what? Overlapping. And it is not what? It is not the atoms that are participating in bonding are actually overlapping, you must understand. No atom overlaps with the other. Remember, they stop at a distance, and it is actually the atomic orbitals which are getting influence, and they actually are participating in the concept of overlapping. You must understand this, right? So the very first postulate, he says that a covalent bond is formed by overlapping of atomic orbitals. It is formed by overlapping of atomic orbitals. That's number one. Number two, he says only those atomic orbitals, there is a condition. There is a condition. Not every atomic orbital can be formed in what? Involved in what? The overlapping. Not every atomic orbital is involved in overlapping. There are conditions set. What he says is only those atomic orbitals where the electrons possess opposite spin. That means you are actually conforming to your Pauli's exclusion principle. An orbital, a compartment, an orbital must be having two electrons, and the two electrons must possess what? Opposite spin. So not every orbital can participate in what? Bonding, and only those atomic orbitals in which the electrons possess opposite spin can actually involve in what? Overlapping. You must understand this. So two things, I repeat again before I actually go into an example, right? The first thing is remember that it is the atomic orbitals which actually participate in what? Overlapping. So a covalent bond is formed by overlapping of atomic orbitals. That's number one. Second point is only those orbitals in which the electrons possess opposite spin will be participating in overlapping. Right? Keep these two in mind and let's go in for an examples. Watch carefully here. Let's take the example of HCl. HCl formation. HCl formation. Let us explain this. Beautifully explained, rather. Observe carefully. Hydrogen electronic configuration is 1s1. Its configuration is what? 1s1. And if you look into the chlorine configuration, it is 17. So if I write its configuration 1s2, 2s2, 2p6, 3s2, 3px2, 3py2 and 3pz1. Remember that. And as a chemist, I have a practice, and you should be also practicing as a chemist. Whenever I write an electronic configuration, I have the habit of underlining the outermost shell, because it is the outermost shell which will be participating in the bonding, not every orbital, at least. So a practice you must be also acquiring is, while writing the electronic configuration, please underline the outermost shell. And shell is designated by the principal quantum number. So it is the outermost shell you need to underline. And the outermost shell is 3. So the entire 3 is underlined, and here it is 1s1. Now what we will do is, we will give a nice explanation by drawing it rather. Look into this. This is the 1s of hydrogen, the 1s of hydrogen atom, and you have one electron, and this is spinning clockwise, right? It's spinning clockwise. You can see here, this is the 1s of hydrogen atom, and that is its configuration. And what I'm doing is, now I'm putting chlorine, and I'm putting not the all orbitals. Not the r orbitals, I will just put the outermost electronic configuration of it. Then if I put it, then it is 3s, 3px, 3py, 3pz. Look into this, the entire outermost shells I have put it, right? And the 3s will be having 2 electrons. You can see here, these are the 2 electrons. I have put it here. And 3px, 3py and 3pz, they are degenerate. They all belong to the p subshell. Whenever electronic configurations are put in degenerate subshells, you must be following Hund's rule. What is Hund's rule? First enter the subshell singly and then go for pairing. Right? If that is the case, in the entire TP you have 5 electrons. So it is 1, 2 and 3 and 4 and 5. Right? That is how I filled according to what? Hund's rule. Now if I apply the valence bond theory, he is clearly telling me that only those orbitals will be participating in overlapping in which the electrons possess opposite spin. And look into these electrons then. This is clockwise, that is anti-clockwise. So I can expect these two fellows to participate in what? The bonding. So that is the bonding, only these two. And forget about this is not participating in bonding. This is not, this is not, this is not, this is not, this is not. And only those orbitals in which the electrons possess opposite spin are actually participating in overlapping. You must understand. When this theory was not there, people were thinking that, yeah, hydrogen atom is coming from here, chlorine atom is coming from there, and both atoms are overlapping. Ridiculous. Silly. So that's why the postulate number 1 says, a covalent bond is formed by overlapping of atomic orbitals, not atoms. It's not atoms, atomic orbitals rather, right? So that's what I'm actually showing here. You can see this is the atomic orbital 1s and it is 3pz, both with opposite spin, and this is the s. This is the s overlapping with the p. So it is basically sp overlap, and that it will be head on. And a head-on bond always results in sigma bond. You must understand. And if we can draw that s orbital is spherical, the p orbital is what? Dumbbell, and it is shown like this. This is the s, 1s of hydrogen with a clockwise spin, and then you have the 3pz, which is dumbbell with an anti-clockwise spin. This is 3pz of chlorine atom. When they overlap, you can see the swelling at the point of overlapping. This is how it looks like, HCl. This is basically the HCl molecule. You must understand. And since this is S, this is P, this is head-on overlap resulting in sigma. So what is my understanding after valence bond theory? What is my understanding after valence bond theory is basically, it is like this. If you want someone to explain HCl and how is this bond formed, this bond is formed by the S and P overlap, and that results in sigma bond. That is the way you need to explain. Instead of that, people were telling me that hydrogen atom is overlapping with chlorine atom, hydrogen atom is overlapping with chlorine atom, and then, you know, that's how the bond is formed. It's ridiculous. It doesn't happen like that. You must understand. It doesn't happen like that. In fact, in hydrogen atom, you have 1s. In chlorine, you have so many people. None of them has actually participated in bonding. None of them has actually participated in bonding. It is only the small, tiny 3pz, which has an unpaired electron, has actually overlapped with the hydrogen atom of 1s of hydrogen atom, and that overlap is binding this chlorine and this hydrogen together. It is the overlap of two tiny S and P in chlorine. They overlapped and the sigma bond is formed. It is not hydrogen which is overlapped with what? Chlorine. It is not like that. It is not like that. It's not like that. Atoms don't overlap. It is the tiny atomic orbitals, that is the S of hydrogen, P of chlorine, not entire P, it is only 3P, Z of chlorine, in which electrons possess opposite spin, only overlap results in what? A bond. And hence HCl molecule is what? Explained. One more thing you must notice, I am not preparing molecules here. Molecules are already there, existing. I am just explaining how this bond can be explained theoretically. Theoretical explanation of the single bond between what? Hydrogen and chlorine. That's what we are exactly doing, you must understand. Let us take an example, second example. Look here. Look here. So that is a beautiful explanation of HCl. Let us explain the second example, please. Watch carefully. Look into this. Formation of oxygen molecule. Formation of oxygen molecule. Well, we all know, oxygen, how does it look like? Its Lewis structure seems to be this. Oxygen in chemistry, remember this, oxygen in chemistry always forms two bonds. It can be two single bonds or a double bond. Each oxygen atom can actually form two bonds. It can be two single bonds or a double bond. In this case, it's a double bond. Now, oxygen belongs to sixth group. It belongs to sixth group. That means that it has 6 electrons in its pocket. So, out of the 6, it has invested 2. So, you are left with 4. Left with 4. And then, in this oxygen, you are left with again 4. But what is happening here is, they are sharing with one another and each have achieved octet. Look at this. And each of which is, this is 2 plus 2, 4. This is 4 and this is 4. This is 8 electrons for this oxygen. And the next oxygen is again 4 and this is 4. This is 8 electrons. So both have achieved what? Octet. Both have achieved octet. And the oxygen molecule is formed. Now the question is, where does the strength come from? It's nice to say oxygen, as you know, both oxygens have achieved octet because they have contributed to one another and they are sharing and both are achieving octet. But where did the strength come from? That's where we need to use the concept of what? Overlapping. Now what I'm doing here is already oxygen is existing with a double bond. Now how is the double bond formed is what we need to explain. So I'm not preparing molecules, mind you, I'm not preparing molecules, I'm just explaining how the bonds are formed. So if I write the oxygen configuration, look here. Oxygen is 8, 1s2, 2s2, 2px2, 2py1, 2pz1. And as a chemist, as I said, I have the habit of underlining the outermost shell. And I'm underlining the outermost shell. This is one oxygen atom. So if I can draw here, this is the 2s, this is the 2px, this is the 2py, this is the 2pz, right, of oxygen. I'm just writing the outermost subshells for you. Other than that, I'm not writing anything. There are other inside, like you have 1s. I'm not interested in that as a chemist because it's always the outermost shells that are actually participating in bonding, right? If that is the case, if this is one oxygen atom, I have the other oxygen atom. This is 2s, 2px, 2py, 2pz. So you have two oxygens. One oxygen's configuration is this. The other oxygen's configuration is that. And now we have to apply the valence bond theory. What does it say? Only those electrons in which the electrons possess opposite spin will be participating in bonding. So let us actually fix that off first. So it is 2s, you have 2 electrons here. And this 2p is split into 3 compartments, that is degenerate. And whenever you're writing configurations in degenerate, you must go in for Hund's rule. So the total p subshell has here 4, 3 plus 1, 4. So if I can write this, 1, first fill half, 3, and then the 4, and then the 4, then the 4. And you can see here there are 2 unpaired electrons now. There are 2 unpaired electrons. And what is valence bond theory telling? Only those orbitals in which the electrons possess opposite spin must be participating in bonding. And you have 2 unpaired electrons now, 2 unpaired electrons. So now get into this. This has 2, and we have to fill 4 again. So 1, 2, 3, and 4. Look into this. This is of one oxygen atom. This is for the another oxygen atom. And look into this. These 2 are clockwise and these 2 are anti-clockwise. And only those orbitals in which the electrons possess opposite spin will only participate in what? Overlapping. That is what is the valence bond theory. And remember, p orbitals are mutually perpendicular. It's x, y, and z. They are mutually perpendicular. Mutually perpendicular to each other. So how to write the pictorial representation of this? Watch here. Watch the overlapping in oxygen. Look into the overlapping in oxygen. Look at the overlapping in oxygen. As I said, x, y, z are mutually perpendicular and y, z have the unpaired. Let us pick these 2 up. This is the 2px. This is the 2py. 2py and 2pz. This is the 2py. And that is the 2pz. And it has 1 electron and it has another electron. You can see here, these 2 I have drawn. They are mutually perpendicular. They are mutually perpendicular. That's for one oxygen. Similarly, you have to draw the other set. Similarly, this is the 2pz and this is the 2py or whatever. Both are what? Mutually perpendicular. Now what did the valence bond theory say? Only those electrons in which the electrons possess opposite spin must be participating in bonding. I mean overlapping rather. So they are ready. This is the overlap and this is basically 2pz overlap, and that results in a sigma bond formation. That results in a sigma bond formation because head-on overlap, 2 heads overlapping, that results in what? Sigma bond formation. That is one sigma bond which you are contributing. That means that you're already explaining this. Oxygen, one bond is explained. This bond is the result of the 2pz overlap, which is resulting in a sigma bond. So this sigma bond has been explained. That sigma bond has been explained. Right? And now coming to the other bond, we need to explain the other bond. So these 2 are parallel. So these 2 will go out for sidewise overlapping, which will result in a pi bond. Sidewise overlapping will look like this. If this is the P, this is the sidewise overlapping. It's not efficient. It's not efficient as a head-on overlapping. You must understand. In head-on overlapping, it is maximum efficient. That's why the sigma bond is stronger than the pi bond. The energy loss that happens in a head-on overlap does not happen to that magnitude in a sidewise overlap. You must understand. So the result of a head-on overlapping, that is sigma bond, is stronger than the pi bond. Is stronger than the pi bond, you must understand that. Right? So you can see here, this and this is overlapping, 2py and 2py. This is 2py. This is resulting in a sigma bond because it is head-on. And this is nothing but the sidewise that results in a pi bond. You must understand that. You must understand that. That is how the oxygen molecule is formed. If this theory was not there, then people have told me oxygen atoms are overlapping with one another. Each oxygen atom is overlapping with the other and a bond is formed. Ridiculous, silly, trivial, whatever. Now this is a sidewise overlap, so this results in a pi bond. So tomorrow if you are explaining someone to your brother or sister at home, can you tell how this double bond is formed? Then you tell him it is not the oxygen-oxygen overlap, but it is the atomic orbitals in these oxygen atoms that are basically what? Overlapping. And this is a head-on overlap resulting in a sigma, and this is a sidewise overlap resulting in a pi bond. Pi bond is weaker than sigma bond because the head-on overlapping is more efficient, more energy lost, more stable, so difficult to break a sigma bond. So I consider sigma bond to be stronger compared to what? A pi bond. What my point? Let us straight away go for another example. Watch carefully here. What we are doing here is, let us take example 3, that is formation nitrogen molecule. Formation of nitrogen molecule. First of all, what we will do is we'll draw the Lewis structures, because I'm not preparing nitrogen compound, they're already there. So the nitrogen molecule, if you see, it looks like this. It has a triple bond, and we need to explain what type of overlapping is happening for the sigma bonds and pi bonds which we are seeing here. Nitrogen in chemistry always forms 3 bonds. 4 bonds rather, but basically it is 3 bonds, right? So it belongs to 5th group. It belongs to 5th group, so it has total 5 electrons in its pocket. 1 it invested here, 2nd it invested here, 3rd it invested here, it has 2. So this nitrogen also invested 3 here, it has 2, right? So the total number of electrons in nitrogen pocket in chemistry is always 5. Oxygen forms 2 bonds, nitrogen forms 3 bonds. You must understand. Now we have to tell how this triple bond is formed sitting in the classroom, because the theory which we are reconciling towards what? The formation of the nitrogen molecule which is already existing. So first let's write the electronic configurations of it. Nitrogen is 7. It's 1s2, 2px, 2py, 2pz, and you have 1, 1, 1. And this is the outermost shell. Nitrogen is, it is 7. 1s2, 2s2, sorry. 1s2, 2s2, 2px1, 2py1, and 2pz1. And as a chemist, I have the habit of underlining the outermost shell. That's what I have done. Right? And then we would like to put it in form of orbitals. Now look into this. This is the outermost shell. This is 2s. This is 2px. This is 2py. This is the 2pz. And s has 2 electrons, so I'm putting it. And the p has 3 electrons, so 1, 2, and 3, because the p subshell is degenerate. And whenever you're writing the electronic configuration in the p subshell, you must follow the Hund's rule. Hund's rule is first get into the p subshell half filled, then pairing occurs. So this is half filled, right? And look into this. This is for the one nitrogen atom. Similarly, if I can draw for the other nitrogen atom, it is 2s, 2px, 2py, and 2pz. And if you can write this 2s has 2 electrons, it is filled. So if I can fill it, 1, 2, and 3. Now look into this. This is for the another nitrogen atom. Now look into this. As the valence bond theory is telling you that only those orbitals participate in bonding in which the electrons possess opposite spin. And here they are ready. And here they are ready. Let us overlap. 2px and 2px overlapping. and this 2px will overlap, and this will be head-on. And that results in sigma. Right? And these two now will be parallel to one another. This is sidewise, and that results in pi. And this also sidewise will result in pi. You must understand. And all these possess opposite spins. Let us give a pictorial for this. Look into this. X, Y, Z are mutually perpendicular. So I draw two sets of mutually perpendicular orbitals. Look here. X, Y, and Z. This is the 2px, 2py, and the 2pz, and you have each electron, one electron here. That's what we have shown. One electron, one. That I have put it there. And you have the other nitrogen, similar to this. This is the 2px. This is the 2py, and that is the 2pz. Look into this. Now they are ready, and here the heads are ready first. This is sigma. So the nitrogen is being formed. This is the sigma. The first bond is formed. The first bond is formed. That is sigma. Head on. And then you have these two parallel. So this will be definitely sidewise. And that is pi. So this is another pi. And the 2pz's are also parallel. This is parallel to this. So this is also sidewise. This is also pi. So this is pi. And the triple bond is formed. And the triple bond is formed. You must understand. So if this theory was not persisting, people would have told me the nitrogen atom is overlapping with the nitrogen atom and hence a bond is formed. So it is not the atoms that are overlapping, it is basically the atomic orbitals that are overlapping. And this atomic orbitals overlapped become a delocalized orbital. Delocalized. Now you are actually roaming in a much larger area. If I ask you to roam in this room and ask you to roam in this entire building, and naturally, when you roam in this entire building, you will lose more energy, and thereby you attain stability. So the atom might contain several number of atomic orbitals. Not every atomic orbital involves in overlapping. It is only those atomic orbitals in which the electrons possess opposite spin will only participate in what? The concept of overlapping. You must understand it. Well, one question arises. Naturally, one question arises. It was so beautifully explained. We understood, and the strength of the covalent bond is derived by the concept of overlapping. We understood. But as I said, whether everyone has merits or not, I don't know. But one thing is sure, that everyone will be having demerits. This fellow also has demerits. Even in spite of explaining beautifully some of the molecules, but still this fellow will be having some demerits, and they are very serious demerits. They are very absolutely serious demerits, which we need to consider and explain. And then once to explain the demerits, I get into another theory, hence the textbook becomes fat, right? So we were beautifully explaining two things in Linus-Pauling theory, that is a valence bond theory. But I'm actually worried. Worried about few things, and that worry is because these come under the demerits. If I ask few questions to Mr. Linus-Pauling, who has explained beautifully all these things, but I have several questions to ask for Linus-Pauling, and he will not be in a position to answer. Thus, I keep this under the demerits heading. So as I said, everyone will have merits or not, I don't know. But definitely everyone will be having demerits. And this fellow is no exception. Mr. Linus-Pauling, in spite of explaining all these beautifully, and he has also explained where the strength of the covalent bond is coming by introducing the concept of overlapping, but still it has demerits. And not only simply demerits, they are very serious demerits. Serious demerits. If I ask questions to Linus Pauling regarding this, he will run away and he will not be in a position to explain all this. So we need to shift ourselves to the other theories to explain. And what are these serious demerits? First of all, let us consider them one by one and then understand why this fellow's theory is only limited but otherwise he will not cover the entire molecules in chemistry. Now what are the merits? First of all, look into this. Let us explain this fellow's theory. You know what are the best merits? Merits of valence bond theory. Merits of what? Valence bond theory. The first thing is, he will be explaining beautifully. Explains structures of, I would like to underline here and I draw the attention over here. I'm writing a word. He is beautiful only to this extent. Not beyond that. He is only beautifully explaining only to some extent. And the extent is this. Structure of diatomic molecules. That's all. He is restricted only to diatomic molecules, not beyond that. And whenever you are restricting to the diatomic molecules, and if anyone who has explained the best, it is Linus Pauling and the valence bond theory. No one can explain better than what he has done. But if you just hang on to diatomic molecules, you are hardly covering 10% of chemistry. Not every molecule is diatomic. They are triatomic, tetraatomic. You have several other molecules. Not even 5% of the chemistry is covered if you just hang on to Linus Pauling, because he has done beautiful things. He has done beautiful things. You just can't what? Hang on here. But the one merit, whatever, whether restrictions are there, whether it's diatomic or whatever, but one thing is carried forward. One thing is carried forward forever in chemistry, forever, for generations to come, is basically the concept of overlapping. That cannot be discounted. That cannot be discounted. The concept of overlapping will be continued for the coming theories. Atoms don't overlap. It is the atomic orbitals inside the atoms that overlap. This concept of overlapping will be continued, extrapolated for all the theories to come. But this fellow has restrictions. He has beautifully explains the structure of what? Diatomic molecules, like this. The hydrogen molecule, which has a single bond, beautifully explained. Then you have fluorine molecule, that is FF, beautifully explained. You have chlorine molecule bond, beautifully explained. Then you have a HCl molecule, that is H and Cl, beautifully explained. Then you have your oxygen, your double bond, beautifully explained. And then you have your nitrogen and the triple bond, beautifully explained. Beautifully explained. But remember, in all this beauty, if you count the number of atoms, there are only two. So he was able to explain the structures of compounds of only what? Diatomic molecules, you must understand. That is his limitation. At the same time, you cannot discount the concept of overlapping. Let me put it proper. It's not the concept of overlapping. It's a concept of overlapping of atomic orbitals, not atoms. Concept of overlapping of atomic orbitals, not atoms. This is carried forward throughout chemistry. So the only thing which is carried forward is basically the concept of overlapping, and otherwise he has only restrictions. He was able to tell us only about what? Diatomic molecules. He cannot explain the other things. You must understand that. Right? If that is the case, and I think if the polyatomic molecules like beryllium chloride, it has 3 atoms, ammonia, water, all these are involving 3 atoms. And the biggest problem involving 3 atoms is, you must even explain the extra thing in this. The extra is the bond angle. Because you require 3 atoms to form an angle, not 2 atoms. What is the angle between these two? There is no angle. For an angle, at least you should say, you know, A, B, and C. Then there is an angle. You must understand. Whenever you are involving 3 atoms, polyatomic, then an angle is coming into place, and you should tell people how the angle of 50 degrees, 60 degrees, 70 degrees, or 70 degrees is formed. And if I ask few questions to Linus Pauling live now, I would like to ask him, what the bond angle in beryllium chloride is 180 degrees. 180. Hey Pauling, can you explain? He cannot. If I ask the bond angle of ammonia is 107, can you explain? He cannot. The bond angle in water is 104, can you explain? He cannot. Even for your methane, which is 109 degrees 28 minutes, hey Pauling, can you explain? He cannot. More than 2 atoms, bond angle comes to play, and the shapes of the molecules are also coming to play. And the shapes are also coming into existence, which Linus Pauling will not be in a position to explain at all. So his restriction is basically to diatomic molecule. When you restrict yourself to diatomic molecule, you need not explain bond angles, not structures. No, sorry, not bond angles and shapes. This is the issue. Well, I would like to take one of them and explain it to you. Right? And it's a failure, not a failure, but miserably fails in explaining few things. Miserably. Well, one example which I would like to take and extrapolate that. Right? But don't develop any prejudice towards Linus Pauling. Don't develop a hatred for Linus Pauling. For one single reason, if anyone has explained where does the strength of the covalent bond coming from, it is of course what Linus Pauling and the valence bond theory. The concept of overlapping will explain to you where does the strength of the covalent bond coming from. And that is a great thing, first ever introduced by Linus Pauling. Don't develop any prejudice just because he has not explained several other molecules. He was able to explain few. And of course the concept of overlapping is the first time introduced by what Linus Pauling. You must understand that. Right? And I'll tell you one miserable failure of what? The valence bond theory. Observe carefully here. Well, formation of beryllium chloride cannot be explained by valence bond theory, which is proposed by Mr. Pauling. Formation of beryllium chloride cannot be explained through the valence bond theory which is proposed by Linus Pauling. Why? Let us see. Let's write the beryllium configuration. It's 1s2, it is 2s2, and you have the entire 2p0 which is vacant. The entire 2p is what? Vacant. And if I can write and split it, the vacancy, it is like this. So it is 2px0, 2py0, and 2pz0. And I have the habit of underlining the outermost shell. The outermost shell. Now what is happening? What is happening is, this is how the beryllium setup is in the ground state. Now what chlorines are doing here, beryllium chloride is BeCl2. The two chlorine atoms are approaching the beryllium. They are approaching the beryllium. When they approach, they vomit energy. The two chlorine atoms which are approaching the beryllium, they vomit energy. Without vomiting, I'm walking from here and there, of course I vomit energy. Right? So similarly, the chlorine atoms approaching the beryllium are vomiting energy. And this vomited energy is eaten away by this beryllium. This vomited energy is eaten away by the beryllium. And when someone is eating energy, they do that in quantums. You must understand. So when they eat energy, they get into an excited state. So the chlorine atoms, when they approach, they give some energy H nu. And this fellow, this H nu is given by chlorine atoms. And it rises to excited state. This is beryllium in ground state. After eating energy, they get into what? Excited state, and one of the s electrons are kicked to p. So the excited state configuration will be like this. One of the s electrons are now kicked to p. And for participating in bonding, you just cannot participate in bonding being in a ground state. You need to get excited. You must be getting excited to participate in bonding. So when the chlorines are approaching, they are vomiting energy. The energy is eaten away by beryllium and it rises to excited state. In excited state, one of the paired electrons in the s is kicked to p. So now you have electrons in s as well as what? P. That is the case of beryllium. And chlorine will be having an unpaired electron in 3pz. If I write the configuration of chlorine for you. This is chlorine. 1s2, 2s2, 2p6, 3s2, 3px2, 3py2, and 3pz1. This is the unpaired electron. And this is how the beryllium chloride looks like this. And we need to explain how this bond is formed and that bond is formed, which cannot be explained by what? Linus Pauling. So beryllium is in ground state and the chlorines approaching it, and the beryllium got excited and kicked one of the s electrons to p. Now you have two unpaired electrons, right? And in beryllium, this is what is happening. In beryllium, you have unpaired electrons in 2s1 and in 2px1. That's what you have. Now what happens? You have two chlorine atoms. Two chlorine atoms. One chlorine atom in 3pz, you have one electron of chlorine. And the other one must be overlapping with the 3pz of chlorine. So now you have two types of overlapping. The one is pp. This will be the pp overlap. The other one is an sp overlap. So two types of overlapping. S and p and a p and p. If I can draw that, I have no issues with P and P, but S and P, now this is the S. This is the S of beryllium. This is the 2s of beryllium. And this is the P of 3pz of chlorine. 3pz of chlorine. And P is a directional orbital, so I call it to be a vector. Now I can't understand one point here. If there is a PS overlap, will it overlap this way? Will it overlap this way? Will it overlap perpendicularly? Will it overlap obtuse? Will it overlap acute? Or this way, or this way, or this way, or this way, this way, this way, this way, this way. Which way? Which way? Which way? Which way is the issue? Which way is the issue? Which way is the issue? The projection of P vector onto S. The projection of P vector onto S is not fixed. Will it be acute? Will it be perpendicular? Will it be obtuse? If obtuse, what angle? If it is perpendicular, what angle? If it is the acute, which angle? Which direction? These things are not taken care of by Linus Pauling. Where? How? 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 This is the S. This is the P. This is this way. Is there anything fixed for you? This way? This way? This way? This way? This way? This way? Which way? Which way? Which way? Which way? So the direction of P onto S is absolutely not fixed. When the direction of P onto S is not fixed, then how can you fix the bond angle? If it is obtuse, you'll have an obtuse bond angle. If it is acute, you'll have an acute bond angle. If it is perpendicular, you'll have a perpendicular bond angle. But if the direction is not fixed, how can you fix the bond angle? It is a miserable failure on the part of what Linus Pauling, you must understand.